All right, welcome everyone. Today we're going to decode what is basically a secret language of the universe. We're going to dig into the physics behind everything from a simple vibration to the sounds that literally shape our world. It's a language written in wiggles, and believe me, by the end of this, you'll be fluent.
So let's just jump right in with a question. What on earth does a guitar string have in common with a medical ultrasound? I mean, it seems like a weird question, right? One makes beautiful music, the other lets us see inside our own bodies. But I promise you, by the end of this explainer, you'll see how they are speaking the exact same physical language.
To understand that language, we've got to start with the very first, most fundamental word, oscillation. Or, as I like to call it, the wiggle. Everything, and I mean everything we're about to talk about, starts right here.
Okay, so picture this, a mass on a spring. You pull it down, you let go, and it just bobs up and down, right? It's not really going anywhere, it's just wiggling in place around that central point of balance. That simple repetitive motion is the absolute foundational building block for everything we're going to discuss.
Now, to really get a handle on any wiggle, physicists use just three key properties. First up, you've got amplitude. That's just how big the wiggle is, how far it moves from the center. Then there's the period, which is the time it takes to complete one full wiggle. And finally, frequency, which tells you how fast it's wiggling. Basically, how many of those wiggles are happening every single second.
And here's the crucial thing you've got to get. Period and frequency, they're basically two sides of the same coin. They're inversely related. So if a wiggle has a really long period, meaning it's kind of slow and lazy, it's going to have a low frequency. But if it has a super short period, happening really, really fast, then you know it's got a high frequency. Simple as that.
So, what's making all this happen? What's driving this whole thing? Well, it's something called the restoring force. You can really just think of it as the universe's own little rule keeper, constantly yelling, "Get back to the middle." It's this invisible pull that keeps the whole oscillation going.
Okay, so up to now, our wiggle has just been hanging out, stuck in one spot. But what happens when that simple little wiggle starts to travel? When it goes on the road?
Well, you get a wave. A wave is basically a disturbance that moves, that propagates, and it carries energy along with it. The best way to think about this is the wave at a sports stadium. The people stand up and sit down, they wiggle in place, but the wave itself travels all the way around the arena. The energy moves, but the people stay in their seats.
And this all boils down to a really elegant little formula, kind of like a recipe, that governs all waves. A wave's speed, its velocity, is simply its frequency multiplied by its wavelength. And wavelength, that little lambda symbol, is just the distance from the peak of one wave to the peak of the next.
All right, so now that we've got the basics of wiggles and waves down, let's zoom in on one very, very special type of wave, one that you and I experience pretty much all day, every day. Sound.
So what is sound when you really get down to it? At its core, it's just a vibration, a wiggle that has to have something to travel through, a medium, like air. It's like a chain reaction of air molecules bumping into each other, a disturbance traveling from a speaker all the way across the room and smacking into your eardrum, making it wiggle too. And this is where it gets absolutely incredible. Our brains are basically amazing little translators. They take the raw physics of that wave and turn it into the rich experience we call sound. So the wave's frequency, how fast it's wiggling, we perceive that as pitch. High frequency, high note. The wave's amplitude, how big the wiggle is, we hear that as loudness. Big amplitude, loud sound.
Now, the stuff that a sound wave is traveling through, oh yeah, that makes a huge difference. Because sound is a mechanical wave, it needs those particles to bump into each other. So it travels fastest through solids, where the particles are all packed together nice and tight. It goes a little slower in liquids, and it's slowest by far in gases, like air, where everything's all spread out.
Okay, but waves don't just, travel in a neat, straight line from point A to point B. Things start to get really interesting, and honestly a little strange, when they begin to interact with the world around them. Oh, you know this one. We all do. It's that classic "meow" of a passing ambulance. That is the Doppler effect in action. As the siren rushes towards you, it's kind of catching up to its own sound waves, squishing them together. That means a higher frequency, which your brain hears as a higher pitch. Then, as it passes and moves away, the waves get all stretched out, the frequency drops, and so does the pitch you hear.
Then we have something called resonance. And wow, this one is powerful. See, every object has a natural frequency that it just loves to vibrate at. And if you can push it or vibrate it at that exact frequency, the amplitude gets bigger and bigger and bigger. It's just like pushing someone on a swing.
If you time your pushes just right, they go flying higher. That's resonance. And it's the exact reason the body of a guitar can take a tiny string vibration and make it loud enough to fill a room. So here's the payoff. Once we really understand these fundamental rules, oscillation, waves, resonance, that's when we can start to harness them. We can build some absolutely incredible technology that puts all these wiggles to work for us.
I mean, take musical instruments. They are the perfect example of this. They are just beautifully engineered tools for creating and controlling resonance and what we call standing waves. By changing the length of an air column in a flute or the shape of a clarinet, a musician can perfectly control which frequencies resonate, which lets them create all the specific notes we know and love.
But we're not just limited to what we can hear. We can also use frequencies that are way, way too high for our ears to even pick up on. That's what we call ultrasound. Sound waves with frequencies above 20,000 hertz. We can't hear them at all, but we can use them to do amazing things, like see inside the human body without ever making a cut. So how does it work? Well, it's kind of like sonar, but for the human body. A probe sends these high-frequency sound pulses into you. Now, as those waves travel, they hit the boundaries between different kinds of tissue, like between your muscle and your bone. At each boundary, some of that wave bounces back as an echo. A computer listens for those echoes, calculates how long they took to return, and uses all that data to build a detailed live picture. It's incredible.
And that brings us right back to where we started. That first question. What does a guitar string have in common with a medical ultrasound? And the answer, it turns out, is everything. They are both masters of the exact same secret language. They both rely on the very same principles: vibration, waves, and resonance. The guitar just uses them to create audible art, and the ultrasound uses them to create invisible sight.
So if there's one thing to take away from all this, it's that the secret language of physics, it is absolutely everywhere. Sound is just a tiny, tiny slice of the entire wave spectrum that our ears happen to be tuned to. So I'll leave you with this to think about. What are their invisible waves? Radio waves from your phone, microwaves in your kitchen, light itself are shaping your world right this very second.